Okay, so today what we're going to do is we're going to begin our next type of distribution, and this one's called the binomial distribution. And there's something in the name that will tell you how to recognize this one, and it's the word binomial. Bi, like bicycle, means how many? Two. So what you're going to happen here is there are only two possible things that can happen. Okay? You go to school or you what? Don't go to school. There's no in between, is there? Right? Okay? Right? You own a cat or you don't own a cat. Yeah? Okay? You broke your thumb or you don't. Do you see the way this works? So that's binomial. You're only offered two choices. And so it's very important that you recognize that. Now, with the other ones, with the Poisson distributions, you had that rate, per or for every or whatever. But these are going to be just two different scenarios. Okay? So let's go to the book and we're going to look at the other limitations, but that's the main one. The other limitations for binomial so that you know that something is the binomial distribution. Okay? So, characteristics of the binomial distribution. Remember, they're going to ask these questions. So make sure you understand not just how to do it, but you also need to know why it's Poisson, why it's binomial. It is a discrete distribution. In other words, the things you're measuring, discrete means they can be counted, right? So you're using counting numbers. So usually it's like how many fingers do you have? Right. So, okay, well, who's on which hand? So here you go. Only had one hand. It doesn't matter. So you can count them though, right? Do you have a third of a finger? Now I recognize some people could, but that's not the point, right? Do you have a third of a finger? No. Do you have a half of a finger, 3/4 of a finger? No. You either have a whole finger or you don't have any fingers for the most part. Now, sometimes it can be fractions though. If you think about shoe sizes go from like 8 to 8.5 to 9 to 9.5. But we're used to that. That's the established pattern. So that's still discrete. Okay? What you can't have is continuous, like the height of the people in this room. Because that can be a range of any height. Yeah? Any decimal, any fraction. So they have to be discrete. You have to be able to be counted. Okay? I don't know why I said counting when I meant counted. Okay? Now, and binomial means that there must only be two outcomes. It's this or that, period. No third choices. Okay? One day I'll stop saying period. Then y'all freak out.
You can say, on God.
Then y'all freak out. You can say what?
On God.
Okay, I probably will never say that. That's okay. But thank you for that, though. Okay, so for example, if you throw a 6, if you don't throw a 6, then you throw a not 6. Anything else, right? And so there can be lots of things that are the not, right? There are lots of other numbers you could throw, but what we're looking at is either a 6 or not 6, right? So don't get confused by the fact that there are more alternatives. You're either looking for a 6, it's either a 6 or not a 6, okay? Conditions that must be met. Must be only two outcomes. The probability of success must stay the same. And I want you to look at the notation for success. They're using pi. But here, they're just using it in the sense that pi is the Greek letter for P. So they're not talking about that 3.14 business, right? This is simply the Greek letter. They use Greek letters and in probability, for sample probabilities. And so for population probability. So just worry about the fact that pi in this case means probability. So don't be thrown by that. You're going to see it in formulas. You're going to see it in some calculators, but not all. Okay. Then the number of trials. Number of trials is always represented by the letter what? N for number. Good. Must be fixed. In other words, you can't have any ambiguity there. You can't do it 5 times this time, 6 times the next time. The number of trials has to be fixed for the binomial distribution. And it can't be less than 0, which sound familiar. That's the same thing as for Poisson. And then whatever you think, but you can go on forever. Okay? So unlike the Poisson where it just kind of stopped, these go on forever. But what you're going to see when we go to the chart is that you go to these huge numbers, but the probability gets so tiny that it's always the same. And I'll show you what I mean by that in a minute. And of course, in order for these to happen, they have to be independent events because just like the Poisson, they can't happen at the same time or you can't do these types of distributions. Right? So remember, you've got to know these conditions as well. Because in order to be able to get the excellence, you have to describe these conditions. And besides that, you have to know them to be able to know which kind you're dealing with. So don't lose these notes. Come back to them frequently. Okay. So what we're going to do is we're going to look at some of these. Again, first of all, they use the formula. Then they show you how to do the calculator. The tables are the easiest way to do these because they're already listed for you exactly what you need. Okay. So the parameters. In other words, parameters mean the things that define what we're looking at. So the pieces of information that we need. The parameters that we need. We need a pi or a p. It means the same thing. That simply means the probability of one event. And we need an n, which again stands for the number of trials. So you must have a probability and you must have a number of trials. And they give you the formula there. Beautiful formula. Everybody loves it, right? The probability that x is a certain number, because we're going to be looking for our x value, just like we did in the Poisson. X is a certain number, is given by this beautiful formula. Yeah, look at it, be afraid, and then ignore it because we're not using it. Okay? Instead, we're going to use the charts. Now, then they go back and talk about the standards and standard deviation and variance. We talked about that before. We're going to revisit it so that you can remember those keystrokes. But remember, part of studying is to study not only the thing we're just working on now, but also going back and reviewing the things that we've done. Unlike Poisson distributions, which were always skewed to the right. Remember, Poisson distributions are always the biggest numbers first, and then they get smaller and smaller and smaller and smaller until they get to nothing, right? So unlike those, binomial distributions can be skewed to the right, skewed to the left, or they can be symmetrical. So lots of different types of distributions here. So you can't really tell that it's binomial distribution by simply looking at the graph like you can a Poisson. So be careful. It is always unimodal, which confuses me because if you look at this one, 2 and 3 have a mode that has the same mode, but oh well, I don't understand. I'll get back to you maybe. Okay, so here we go. Let's look at a problem. We're not going to do it their way. 25% of the bones in your body are in your feet. If 5 bones from your body are selected at random, what is the probability that 3 are from your feet? So we either have feet or what? Not feet. Right? So that's 2 choices. So the probability is 25%, so they changed that to a decimal because you're going to have to change it to a decimal to be able to use it. The number is the trials is the number of bones they chose, and how many did they choose in this case?
5.
They selected 5, so that's the number of trials, right? The number of items we're choosing. And what is the probability that 3 of those 5 are from your feet? So our x is a 3. Okay? Now, you could put it in the formula, and if you do, you're insane. If you could put it in a list, if you do, I don't understand why you'd want to do that either, because you have this beautiful table in the back. Pi is another way of saying what? Probability. So our probability was 0.25. Okay. N is, so you'll see there's an N and an X. So there's 2 numbers in these columns now. So our N was 5. And our x was 3, so we look at the 5, 3, and go over, and we get probability that x is equal to 3 is 0.0879. So you're just reading from the chart. Now the difference between this chart and the last one is, again, the probabilities are at the top, just like last time, but, the probabilities were in the field, sorry. But the probabilities are on the top. You have an n and an x, and they're both read in the same column, right? So we had an n of 5 and an x of 3. So find the one, so it's broken down as you go down, and they're always in order. So it's 4, 5, 6, 7, whatever. And then each one has the numbers associated within it. Now notice that they get more as the probability gets higher. You have more options. So just like the last chart we worked with. Okay. So here is the probability of 3 given those parameters. Okay. Answer in a sentence. The probability that 3 out of the 5 bones are from the feet is 0.0879. If you give the correct number, that's achieved. If you answer in a sentence, in other words, in context, that's your merit. All right? So just being able to answer in a sentence is really good. Okay? So we're going to use these tables to answer these questions. So let's look at another one. Only 10% of the cells in the human body are of human origin. Does that confuse you? 10% are of human origin. The rest are mostly bacteria and fungi. If 10 cells are selected at random, so what does that tell you? The number that we selected at random, so our N is what? 10. There you go. And what is the probability that more than 2 are human? So this time we have more than 2, right? So the probability that they're human is what we're looking at is 10%. So can't use that as 10%, so we'll change it to a decimal, right? The number that of cells we're going to select are 10, so that's our N. And we're going to look at X no more than 2, okay? Or is more than 2, I'm not sorry. So X of more than 2. And that means does that mean it includes 2 in this case? No. So this time we're looking more than 2. So we're talking 3 and up, right? So you're going to see that little tiny piece business coming in. If that's the case, it's going to be more than one answer. So what am I going to do when I go to my chart and I see my more than one answer? What do I do to all the answers? Add them up. Right. Good. Okay. So we have all our pieces. Let's just forget the formula. Forget the calculator. If you want to do it using a calculator, go ahead. It's harder. All right. Let's go to the chart. So here we have our table, and up there at the top, what they've left off, they've cut it off because it's way down at 10. Right at the very top of the table, you'll see the probabilities across the top, and so we went to 0.1, and then 10 was our number, and we want everything else. Now look at what they've done. We want everything else, which is the bottom part. They did the top part in this case. Because remember that if you have a bunch of numbers to add, you have 2 ways to do it. I could have done 3 and everything above 3. Right? That's what we're looking for. But that's several numbers to add together. And if you look down here, it says all other entries are less than 0.0001. But we still want to account for those parts. So in this case, it's easier to add what I don't want and then subtract what I don't want from what? 1. So 1 minus what I don't want will always equal what you do want. So if you have a lot of numbers to put together, or there's some ambiguous stuff, then find out what you don't want, subtract it from 1, and it'll get every single part of it. Right? Remember we did that on Poisson as well. So if you find out what you don't want, subtract it from 1, it'll give you what you do want. Get used to using that piece because it's critical to being able to do some of these questions where they already asked you. They gave you a part where you don't want this, so what is it you do want? Okay? So we added those together and subtracted from 1, and it gives you 0.0702. Okay?
Why does it only go from 4 to 10? Why is 1, 2, 3 not included?
Because these get so tiny down here. Do you see here?
Yeah.
At 6? It's already at that tiniest little bit. All the rest of them are going to be that same number. Actually, smaller than that small. They're going to be so tiny that who cares? Right? So it only goes down. Now, you see this one, it didn't get tiny until you get down here to 7. And some of the bigger probabilities, as the probability gets bigger, you're going to see the list gets longer.
Wait, do you want us to just use the table when...
Absolutely. Just use the table.
Use the calculator?
Don't use the calculator. Don't use the formula. Just use the table. Your life will be so much easier if you just use the table. Okay? And again, you're going to have the table, so practice using it. Okay. So let's look at one. All right, so here's the one where they just went ahead and added all those numbers. This one, it really didn't matter because you were only adding one more number than what you had. And you see you get the same thing by just adding. But get used to that one minus business. All right, so today what we're going to do is I just want you to practice finding probabilities from the table, finding the answers from the table, and getting used to the terminology. Like if it's x is less than 2, what does that mean it's going to be? Right? So less than or equal to. So all we're going to do today is we're going to do number 1 and number 2 on page 50. Right? And if you look, the n and the probability stay the same for the whole thing on that one, and then they do a different n and a different probability for the other. So what you're really practicing here is what values can x be, and what would the probability be for that particular value. Okay, there you go.